Hello, Marina.
Hi, Ben.
Dale, are you hiding in your hotel room?
Yeah, I have like 20 minutes or so, and then I have to go. So.
I'm muting myself.
Marina, I'm so sorry. I was introducing you on being muted. So I turned on the recording and I started on time. Sorry about that. So let me repeat it everything again. So today we have our pleasure to have Marina Battaglia as speaker at our webinar, who is currently since 2014 is lecturer at the University of Applied Science Northwestern Switzerland. Previously, she served as PhD at ETH Zurich, Leverhulme Research Fellow at the University of Glasgow. She was postdoc at the University of Applied Science at Northwestern Switzerland. Her research interests are studies of electron acceleration and propagation and atmospheric response through multi-wavelength observations. Now she is an important part of STIC's team at FHNW, which is Institute for 4D Technology, I believe. So please, Marina, go ahead with your presentation. I will give a warning 5 minutes before the end, and will interrupt only if needed. So please go ahead.
All right, thank you, Gregory, and welcome everybody. So as Gregory said it, I'm focusing on multi-wavelength observations of flares and their effects on the solar atmosphere. And today I'm going to focus on X-ray and UV observations in particular, and how we can combine them to learn something about electron acceleration and propagation in solar flares. So here's the outline of what I'm going to talk about. I'm just quickly going to remind everybody of some of the important open questions we have in solar flare physics. Then I'll briefly revise the standard solar flare scenario, as I like to call it, give you a brief overview of the emission mechanisms we're dealing with when we're looking at X-rays and UV. And then I want to give you two examples of what we can learn by combining UV and X-ray observations. One is about electron acceleration, in particular the distribution and energies of accelerated electrons. And the other is chromospheric response, what we can learn about chromospheric evaporation. So here are two movies of flares as you can see them in EUV, this is AIA 131, a nice flare near the limb. Here we have AIA 171, a filament eruption, and to the north of it, we have X-ray observations with RESI. Blue is non-thermal, so that's signatures of accelerated particles, and the red is thermal emission from the hot loops. So some of the open questions we're trying to answer are, where are electrons accelerated? Then, of course, what is the total energy that is contained in a flare? How are electrons accelerated? Then transport of electrons, are they trapped? Are they reaccelerated in the loop? And then also what happens to the chromosphere, to the solar atmosphere, once the electrons deposit their energy. And so in this talk, I will try to give some answers to these questions about the where electrons are accelerated, about total energies in the flare, and about the chromospheric response. So how do we picture a flare happening? What I'm showing here is the standard cartoon by Shibata. We are pretty certain that we have magnetic reconnections somewhere in the corona. Electrons are accelerated, electrons and protons are accelerated on the one hand upward away from the sun, and on the other hand downwards towards the chromosphere. There they deposit their energy, which leads to overpressure and a rise of hot material that fills out these loops. Now, whenever I show this cartoon, I show this with a disclaimer. It's one cartoon of many. If we can agree on something in the community, then probably that we don't agree on a cartoon. So if you want to see more cartoons, I suggest you Google Hudson Flare cartoons or go to this link, and you will find all cartoons that have been published in the past decades. So you see there are about as many cartoons as there are authors. But the main point remains, we accelerate particles somewhere in the corona and they travel downwards towards the foot point and heat up the lower layers of the solar atmosphere. So the emissions that we expect in this standard solar flare scenario, now focusing entirely on X-ray and EUV emission. Of course, there are others, in particular radio, but since this talk is about X-rays and EUV, this is what we expect in the standard solar flare scenario. So we have reconnection somewhere here. Particles are maybe accelerated near the reconnection region as well, maybe somewhere up or somewhere down. Then we have the accelerated particles traveling upwards and downwards, and the loop that fills up with hot material. So in this scenario, we would expect hard X-rays from the foot points in the chromosphere, but also from somewhere up in the corona, since we also have accelerated particles moving upwards. Except this emission is very difficult to observe since it's a low density plasma up here, so the intensity of the produced X-rays is quite low. So X-rays allow us to probe the acceleration region, at spectrum of the accelerated electrons, and the total non-thermal energy. Then we often see a soft X-ray coronal source that outlines the hot top of the magnetic loops, and the magnetic loops we see outlined in UV as well. And finally, we have optical and UV emission from the photosphere, the chromosphere, and the transition region that allows us in particular to investigate plasma flows, evaporation flows, coronal rain, etc. So by combining these wavelengths, we can learn a lot about the flare. What the mechanism that causes this emission for Bremsstrahlung, it's for X-rays, it's Bremsstrahlung. So you have an accelerated electron that is diverted from its path by a proton, and it emits an X-ray photon. This is an idealized X-ray flare spectrum from the original RESI book that shows you what in the perfect world we could observe. So at low photon energies, the spectrum is dominated by thermal Bremsstrahlung. Then we have the non-thermal tail that typically has the shape of a power law from the accelerated electrons. And then in the gamma ray range, we have the ion lines. As I'm focusing on the low energy part, let's have a look at an actually observed spectrum of a solar flare. Again, you see the UV loop. Then we have hard X-ray foot points in the chromosphere. As expected in the standard solar flare scenario, we have the coronal thermal source up here. And in this particular flare, it was also possible to observe hard X-ray emission from above the loop top. That is fairly rare, but in this case, it was possible. And as you can see, the spectra of these different sources have different shapes. The thermal spectrum allows us to infer the temperature and the emission measure of the hot plasma, and the non-thermal spectrum allows us to infer the total number of accelerated electrons, the energy they contain, and also in this case, we interpreted this source to be the acceleration region. In EUV, we mostly observe line emission. This is an example of the famous best observed flare observed with iris. So this is an iris slit jaw image where you see nicely two flaring ribbons. And then two examples, one is magnesium 2 and one is iron 21, that here brightens clearly as the ribbon brightens as well. So this emission is from partially ionized ions in the solar atmosphere, and these lines form under different conditions, under different temperatures and densities. So they allow us to probe essentially the whole solar atmosphere from the photosphere up to the corona. This is an example focusing on this iron 21 line. This dashed line gives the rest wavelength of this line, and in this case you can see it was shifted to the left, meaning that hot plasma was flowing towards the observer, was blue shifted, so it was flowing upwards towards the observer. The first example I want to talk about of how we combine these observations is about electron acceleration, in particular the distribution and the energies of accelerated electrons. Now the challenge we face is we want to infer the mean electron flux spectrum over, of course, the largest possible energy range. So if we have, say, a flare like this, a single flaring source, we observe the RESI spectrum, and from an isothermal fit and a same target power law fit, we can infer the mean electron flux spectrum. So that would then look something like this. But since RESI is only sensitive to certain photon energies, of course we are limited in the accessible energy range. In particular, this low energy part is not very well accessible, but it carries a lot of the total flare energy. So what can we do? We can use AIA to extend this energy range down to the lower energies. From AIA, we have observations at 6 wavelengths sensitive to coronal temperatures, and we can determine the differential emission measure. So the emission of a multithermal plasma as a function of temperature. And now the neat thing is that the mean electron flux spectrum is directly related to this emission measure. So once we have the emission measure, we can work out the mean electron flux spectrum and then basically attach what AIA tells us to what we found from RESI, and that gives this picture. So by combining these observations, we can extend the energy range down to about 0.1 keV. Now, as you can see, this is quite the patchwork. So we can do better than that, and we did. The idea is that one combines RESI and AIA data and do a simultaneous fit of both data sets. The ingredients you need for these are the AIA counts in the 4 wavelength channels. You need your RESI spectrum. You need a combined temperature response matrix and some sort of a fit function. And you shake it thoroughly and out falls your mean electron flux spectrum. Now, in reality, things are not as simple. So let's go back one step. We want to treat RESI and AIA data as one data set. The underlying idea is that any signal, be that X-ray or EUV, is essentially the convolution of the temperature response, the differential emission measure, and then the bin width, the temperature bin width of your instrument. So this allows us to generate one single temperature response matrix that looks something like shown here. So your first 6 columns rows would be the AIA temperature response, and then you add your RESI detector response times the isothermal Bremsstrahlung function. Temperature responses are shown here, so this is AIA and this is RESI for different energies. And then you can forward fit a model differential emission measure, and once we have that, as shown previously, we can then infer the mean electron flux spectrum. Now we have to choose a fit function that we want to use. And one that basically offers itself is the kappa distribution. So for those not familiar with this, the standard approach we use is we fit a thermal component plus a non-thermal component that consists of a flux normalization, the slope of the power law, the spectral index, and then we need some sort of a cutoff energy, because otherwise the energy in this non-thermal spectrum would become infinitely large. So these are then 6 parameters in total that are fitted. Now the kappa distribution is basically the combination of the two. So you have your core and then a tail that just rises out of your core distribution. And you have 3 parameters, the kappa temperature and the kappa emission measure, that define this core, and then the kappa index that defines the slope of your extended component. Now, why we use kappa? There are several reasons. For one, it is a single analytic function that describes the whole spectrum, which is what we want. We don't need this electron cutoff that is notoriously difficult to determine. many stochastic acceleration models yield kappa distributions, and they were observed in multiple RESI observations as well. Plus, another bonus is we can actually express the kappa distribution as a differential emission measure. And then, as I said, once we have that, we can infer the non-thermal electron flux distribution. Now, this is basically just a mathematical representation of the spectrum. So we're not saying that the plasma contains temperatures of 100 megakelvin, say. We construct the spectrum to consist of basically these temperatures to yield a function that is the kappa distribution. And this is the example application on this single loop flare. To the right, you see the differential emission measure. Up here are the loci curves from AIA. The gray area is the AIA differential emission measure as found using the code by Ian Hanna and Elber Kontar. And the red curve is the result of our joint fit. Now, in this case, we had to use two components, two kappa distributions, one to account for this component and one to account for the green component. The green component, low temperature component, is predominantly foreground or background coronal emission, and the high temperature component is the actual flare emission. From the DEM, we inferred the mean electron flux spectrum that resulted in the following picture. The red is the total flux spectrum from the combined DEM fit. And in comparison, I also show what happens when one only uses RESI data, but fits the same kappa distribution. And I also show what happens when one fits the thin kappa function that is built in the RESI analysis software. So the main point to take away from this is at these lower energies, using this combined method, we get a lot less electrons than when using RESI only. And that affects the total energy that is in this flare. So we can calculate, first of all, the total energy density, and then the total energy by multiplying with the volume. And as you can see, when using RESI only and fitting the original thin target kappa distribution, we get a factor of 5 higher energy density than by using this combined method. So the bottom line of this is, without this low energy constraint that AIA gives us, we may be overestimating the total energy in the flare by up to a factor of 5 if we only use RESI data. So this was mostly a proof of concept, and now we can apply this method on an old acquaintance that many of you are probably familiar with. That's the flare that happened on July 19th, 2012. And there were quite a lot of papers about this flare focusing on different aspects of the flare. And it is a very interesting flare. So here you have the light curves of this event. The impulsive phase happened at around 5:20 UT. So if we go backwards from this phase and look at images, this image was taken during the main impulsive phase, where you have your coronal source and one foot point. The other one was most likely occulted, as you expect from the standard flare scenario. Going back 15 minutes, This is what you see. Again, the UV loop and some thermal emission from RESI. Now going even further back, so now we're around here in time, this is what you could observe. So it was actually possible to image two sources with RESI, one above what can be presumed to be the reconnection region and one below. So this is quite rare, and this happened way early in the flares, so up to 50 minutes before the impulsive phase. So we focused on these 15 minutes here where we had the two sources and used this combined RESI AIA fitting method to investigate the spectral evolution in both of these sources. This is the result from this joint fitting. So the mean electron flux spectrum in the source below the acceleration region or the reconnection region and in the source above. You can see the evolution of the spectra in time is quite different. Times are given here to the right, so we start with the black and then move up through the colors to the purple. So in the source below the reconnection region, the whole spectrum rises as time progresses. And this spectral index of this tail is very steep and remains almost constant. Above the reconnection region, at the lowest energies, the spectrum remains constant, but this tail becomes increasingly flatter, so the spectral index becomes smaller as time progresses. So here we see a continuous hardening over time, but in the source below, we have an overall rise. Now this can be interpreted as following. In the source above the reconnection region, we see electron acceleration. Electrons are accelerated to progressively higher energies that results in this hardening of the spectrum. While as in the source below the reconnection region, we most likely have a density increase due to evaporation from the chromosphere. We can also investigate the total energies in these sources and the losses, energy losses out of these sources. In this case, we have two dominant means of energy loss, of energy transport out of the source. One is by conduction and one is by free streaming electrons. Radiative energy losses in these conditions are several orders of magnitude lower, so they can be neglected. So we calculated the energy loss due to conduction and due to free streaming electrons out of both sources. And the result you can see here. And these energy losses are actually fairly large. Remember, this is the pre-impulsive phase of the flare. I'm comparing them with some results from the literature, mainly from Warmuth and Mann. They analyzed the main phase of the flare. The red are the conductive losses and the blue are the non-thermal free streaming losses they found. And I'm also comparing it with another event I investigated, the pre-flare phase of an event. And as you can see, the energies are quite comparable. So this suggests that even this early in the flare, we have very efficient acceleration of electrons, and this pre-impulsive flare phase is very important when it comes to overall flare energetics, because already here we have a lot of energy that is released and converted into other forms of energies. So this is something that you could not do in this detail by only using RESI observations or only using AIA observations. Now moving down in the solar atmosphere, the second example I want to talk about is the chromospheric response, in particular the chromospheric evaporation as seen in X-rays and EUV. Going back to this standard flare scenario, we have electrons that are accelerated downwards to the chromosphere. They hit the chromosphere, deposit their energy. This leads to overpressure in the chromosphere and to heating, and that drives a plasma flow upwards, which was termed chromospheric evaporation. It's the term we use, although it's technically not correct. There's nothing evaporating in the strictly thermodynamical sense. It's just plasma flows upwards along the magnetic fields, filling out this loop that then becomes visible in the UV. So by combining X-ray and UV observations again, we can learn something about this evaporation, about these flows. This shows some early work by Milligan et al. They investigated the velocities of the evaporating plasma using Hinode eyes. What is shown here are a number of spectral lines that, as I said, form at different temperatures. The white contours indicate X-ray, hard X-ray footpoints observed with RESI. Red means plasma flows away from the observer, downwards, and blue means plasma flows that are blue shifted upwards towards the observer. And they analyzed the velocities as a function of temperature and found the following. At higher temperatures, you have blue shifted negative velocities towards the observer of the order of a few hundred kilometers per second. And at lower temperatures, you have plasma moving away from the observer, moving downward. And this is what one would expect when evaporation is triggered by energy input through to a non-thermal electron beam that carries a lot of energy. What you get in this case, if this energy is high enough, is what was termed explosive evaporation. It means that due to this energy deposition, you construct an overpressure that drives the cooler plasma downwards, and the hotter plasma moves upwards. So this is what you would expect in this case. And the RESI observation here confirms that actually there was a strong electron beam with quite a high energy that could have triggered this evaporation. The second example focuses on iris observations that were combined with RESI observations. So with iris, we have fairly high spatial resolution. And in this particular flare, again, that was the GOES X1 flare from March 29, 2014, that was observed with pretty much all the instruments. The light curve of the event looked like this. So the green is the GOES, and the red shows the RESI hard X-rays. And we focus on this part during the main hard X-ray phase. In this particular case, you can see two flaring ribbons. This is from an iris slit jaw image, one ribbon here at the south and one ribbon at the north. The RESI hard X-ray source moved basically as the ribbon moved as well. So it started out here and then moved downwards to here. IRIS was in the rastering mode. That means it rastered across this whole region, starting here, and then in steps indicated by these colored dashed lines, it rastered across, and then you basically step back and start over again. So we had simultaneous observations with RESI and with IRIS, and we analyzed the IRIS observations of the iron 21 line, which forms at about 10 megakelvin. And this is what you see. So each of these images is from one IRIS scan across. So that's actually taken over a bit more than a minute and then stacked together. Blue indicates upflowing plasma, and red indicates redshifted downflowing plasma. So you can see how the ribbon is very nicely lined out here, the southern ribbon, and this bit of the northern ribbon that was just caught by the first slit position. The redshifts may not actually be real. They could suggest that the loop is contracting somewhat, but it could also be due to projection effect. And in any case, it's very slight. Focusing on the ribbon, we can now overlay the location of the hard X-ray emission of the RESI source at the same time. So this gives us the location of where energy is deposited as a function of time. As you can see, from about 1748 onwards, we could not image the RESI source anymore. Also, there was not much hard X-ray emission in the light curve or in the spectrum that indicates that from here on out, not many electrons were accelerated anymore. But still, you have clear upflows, evaporating plasma at 10 megakelvin from the ribbon, even a few minutes afterwards as well. So how can we interpret this? Here are some more details of the RESI source and where the IRIS slit was at the same time. So they did not always coincide, of course, because IRIS rastered across. There were some times when we saw the RESI source exactly at the same time as the IRIS slit was over the same location. And then it would move on further. So from this observation combined, we can say there are clear upflows along the flare ribbon, as you would expect from chromospheric evaporation. The speed is of the order of 200 kilometers per second. That's a reasonable number. But these upflows are sustained several minutes after the hard X-rays have ceased. So somehow this evaporation is sustained and continues going. So the interpretation of this event was during the main hard X-ray phase, when a lot of particles are accelerated, the chromospheric evaporation is predominantly driven by an energetic electron beam. Now, by the time this acceleration has ceased, we have a fairly hot coronal source and we have a strong temperature gradient. So it's quite likely that during this phase here, evaporation continued, mostly due to conductive energy input from the loop down to the chromosphere that allowed evaporation to be sustained. So these were the two examples, actually a bit ahead of time. The summary and conclusion is very brief. I hope I could convince you that we need to combine observations at EUV and X-ray wavelengths to really get a good understanding of particle acceleration and transport in solar flares. And combining this with new methods of data analysis, like this combined fitting, further improves our understanding of these processes in the flares.
Okay, thank you, Marina. It was very, very interesting talk. Now we are open for questions. Please unmute your microphone and ask a question if you have any. So far, I don't see any unmuted microphone. But maybe let me ask you like one question. Recently, we had a presentation by Natasha Jeffrey within this webinar series, and Natasha was talking in particular about non-thermal fit on thermal analysis of UV line profiles, and in particular she advocated in favor of fitting of line profile with kappa function, and she derived kappa distribution which might be interpreted as a distribution of ion velocities or ion energies. Do you know about any comparison in one single event between kappas derived for ions and kappa derived for electrons? Are they consistent, or do they expect it to be consistent with each other or not at all? So can you comment at all this?
I don't know of any study that was made in this respect. It would certainly be interesting to do so, I guess. I think from RESI observations alone, we can say that electrons and protons are not necessarily accelerated the same way, or they're not transported the same way. There was this famous RESI result that showed signatures of accelerated ions and protons from a different location than the electrons. So I don't know whether we could expect the distributions to be the same, but it would certainly be interesting to look into that in case we have an event where this can be done.
Yeah, I think it would be interesting to at least to look at it at first place. More questions from people?
I've got a question, of course.
Yeah, Hugh, go ahead.
So, it's very nice to be able to combine the spectrum from the soft X-rays and the hard X-rays into one grand overview kind of thing, the way you described. But if you look at the images, you see that these sources are in different places, and so the assumption that they're the same source is always a very strong assumption. Do you want to comment about that?
Yes, I should have added this. Of course, you can only do that when you can make a strong case that you are looking at the same source. So for the single loop source, this was certainly the case. And for the pre-impulsive phase that we looked at, we did RESI imaging spectroscopy, of course, to isolate the two sources and to separate them properly from each other. In your average standard flare, this may be difficult. So it works best when you either have just one source or when you can do imaging spectroscopy with RESI to separate individual sources.
Well, I understand that, but of course the resolution of our telescopes is really not very good, and very often we don't resolve these sources well enough to be able to say. So I think there's always room for a filling factor or an upper limit kind of analysis along these lines, as opposed to just a strong assumption, too strong that they're always in the same place. Anyway, thank you very much.
Okay, thanks, Marina. Other questions from listeners. I have minor technical question. When you estimated thermal energy, you used as a coefficient 3/2. So do you just expect that only electrons are being heated, not protons, or you just wanted to estimate exactly what you see?
Yeah, so this is just electrons, and it's not just the thermal energy, it's the whole energy. But since the kappa distribution is described via the kappa temperature, which is essentially the average kinetic energy of all the particles in the distribution, this is how you end up with. But it's only the electrons. We cannot say anything about the protons from these observations.
So Marina, I have a question.
Bin, go ahead.
So the non-thermal, the energy during this pre-impulsive phase that you presented is pretty high, something like 10 to the 28.
Ben, you're hard to hear.
It's hard to hear me? Sorry, I'll speak up. So the energy loss rate estimated for the pre-impulsive phase is somewhere between 10 to the 28 and 10 to the 29 ergs per second. And actually, I read your paper, and you indicated that in order for the energy release to account for this energy loss, you need a minimum magnetic field strength of at least 200 Gauss or so at a location, I think that's 50 to 100 arcsecond above the surface. That's very interesting because that's what we found in our user data.
Exactly.
So if that's the case, do you think the pre-impulsive phase is actually the phase that releases most of the energy, or is the maximum, the soft rate maximum is the phase?
Maybe it's not the phase where most of the energy is released, and it may not always be the case in all the flares, but I think we should not underestimate the pre-impulsive phase. I think it's important, and it contributes considerably to the overall energetics.
Bin, I can remind you that even for Marina's set of events, which were treated as entirely thermal, pre-impulsive in 2009, I believe, or so, when we analyzed radio, we found that non-thermal component was already there at this pre-impulsive phase. So the reality, of course, is much more complicated than just thermal pre-flare and like impulsive flares. So basically, everything can be mixed over all phases in general case, at least. Yeah.
Well, just a quick estimate. I mean, with this energy loss rate multiplied by 10 minutes, at least 10 minutes in the pre-impulsive phase, already give us 10 to the 31 ergs.
Yeah.
That's 10 to the 32 is like the X flares, large X flares. So that's why I'm asking. Maybe the pre-impulsive phase is one of the important phases that release a lot of the energy, which has been sort of ignored.
Yeah.
in studies. So it's very interesting.
Good, thanks. Been other comments, if any? Okay, it seems that we do not have any further comments. I meant to tell to the listeners that in principle next webinar is scheduled for May 1st. At the same time, I realize that this is day off in some subset of countries, including Japan, this year, because they have like important transition from one empire to another, and they have long holidays during this period. So I'm not yet sure that the webinar will happen on May 1st. Those who are interested, please contact me, and otherwise I will send out a Solr news announcement for the next issue for April 15 with final decision about May 1st event. The following one will happen, I believe, as scheduled May 27. Yeah, May 20th. I think so, end of May, basically. So thank you very much, and join us again. Thanks, Marina.